My name is Yeoul Na. I'm leading a compiler team at Apple focused on memory safety for C. And I'm extremely honored to present as a keynote speaker today. Thanks, Tanya and LLVM organizers for offering me this great opportunity. Today, I'll talk about bound safety, a C extension to enforce bound safety for production C code. And this is something Apple has been using for several years to secure our production C code. And it's been working pretty well, so I'm very excited to share this with you today. We are planning to upstream our work to the LLVM project soon, and we'll be bringing up our RFC very soon. We are also interested in standardizing it for C standard in future, and I'd love to hear all your feedback. Here's today's agenda. I'm going to give our motivation and talk about our design goals and challenges. Then move on to the programming model, and I'll talk about optimization and performance impact. Memory safety bugs have been the leading source of security vulnerabilities. Across the industry, memory safety vulnerabilities account for 2/3 of entire software vulnerabilities. And historically, many high-profile attacks have exploited memory safety vulnerabilities to gain full remote control over the victim's devices, leading to financial and physical threats. Memory safety can be achieved by securing these 5 properties: bound safety or spatial safety, temporal safety or lifetime safety, type safety, definite initialization, and threat safety. Unfortunately, the C language doesn't guarantee these safety properties by default. It is up to the programmers to add necessary bounds checks or necessary checks to ensure their code is safe. And history shows that even the most skilled programmers will occasionally make mistakes, and that those mistakes can have dire consequences. We have memory-safe languages that are designed to offer enhanced safety guarantees. They tend to provide the first 4 properties and also providing varying levels of support for threat safety. So for enhanced security, memory-safe languages are the best option. Memory-safe languages have emerged as promising options for systems programming. They are becoming increasingly available for more and more programming environments. And there are a lot of incredible initiatives taking place in this area. Here at Apple, we also invest a lot in this domain to enhance the availability and capabilities of the Swift language. However, there are billions of lines of C code in production out there. While there are efforts to rewrite existing C code with safe languages, such as in the case of the Linux kernel, it can be rewritten just in one day. Rewriting such a complex and massive code base will require significant engineering time and effort. This means we will continue to maintain the remaining C code at least for several more decades. So we need a solution to rapidly make all these existing codes safer today. Especially, we need to do something with bound safety. Bound safety violations have been one of the most biggest causes of dangerous software vulnerabilities. In the 2022 CWE Top 25 Most Dangerous Software Weaknesses shows that bound safety issues were ranked top on the chart, including intra-object buffer overflow, and improper input validation and integer overflow, which frequently leads to out-of-bounds memory accesses, were also ranked high on the chart. For this reason, we are proposing bound safety, an extension to bring bound safety to C. The extension only provides bound safety, So for comprehensive memory safety, you should use memory-safe languages. However, our extension offers a quicker way to make the remaining C code safer today. Now let's talk about our design goals and challenges. In fact, many programmers manually add bounds checks to avoid bound safety bugs, but they sometimes make mistakes. They might forget to insert necessary checks or do so incorrectly. In this code example, the for loop condition check has an off by 1 mistake, and this leads to out-of-bounds memory access during the final iteration. To tackle this problem, the bound safety extension automatically inserts bound checks right before every memory access as a safety net. And yeah, this seems to be a very reasonable thing to do. In fact, this is what most memory-safe languages already do. But for C, it's still a difficult problem. The reason is that pointers in C do not have bounds information that the compiler can use to automatically insert checks. One potential solution is using white pointers. White pointers are a pointer representation that internally has bounds information alongside the pointer value. This is also known as bad pointers. Since a white pointer has bounds information, the compiler will always be able to insert bound checks. However, using white pointers breaks the application binary interface, as it makes the pointers bigger. This causes problems when the project interacts with external libraries, which would expect the pointer to have the standard representation. And for similar reasons, breaking the ABI also makes it difficult to incrementally adopt the technique, because code with and without the technique will have different pointer representations. However, the ability to adopt incrementally is crucial. Adoption often requires significant engineering effort. In real-world environments with limited time budget and complex code bases, adopting a new language extension on a large project all at once is likely infeasible. Thus, instead of storing bounds information inside the pointers, another potential solution would be to use bounds annotations that programmers can use to provide bounds information on every pointer. For instance, using some kind of annotation on buff to indicate how many elements it has. And that way, the pointer doesn't need to change its representation to host additional bounds metadata. This will allow us to preserve the ABI and facilitate incremental adoption. But still, the problem is that adding bounds annotations on every pointer requires significant programmer effort. This can be a key bottleneck for wide adoption in practice. So the bound safety extension solves these problems by mixing the two approaches together and taking only the benefits of the two. The extension uses white pointers on non-ABI surface to lower the adoption burden. While the extension provides bounds annotations, the programmers can add on the ABI surface to preserve the ABI and enable incremental adoption. This is bound safety. And let me show you what the programming model really looks like. The bound safety extension provides bounds annotations that programmers to adopt on function prototypes, struct fields, and globals. Using this bounds information, the compiler inserts bound checks. Programmers must provide sufficient bounds information. Otherwise, the compiler will reject the code. and will guide the programmers to add necessary bounds annotations. In this example, the parameter buff doesn't have necessary bounds information, so the compiler rejects the code by reporting an error when the buffer is used for array access. To make this code work, the programmer needs to add a bounds annotation so the error can be removed. This way, the extension effectively secures all pointers by default. However, in many cases, the extension doesn't require bounds annotations at all. Most local variables don't need bounds annotations because the compiler can implicitly carry the bounds information without impacting the ABI. In this example, the local variable buff takes bounds information from the right-hand side of the assignment without need for explicit bounds annotation. Behind the scenes, the compiler implicitly treats this local pointer as wide pointers to store bounds information. This doesn't impact the ABI because the local variables are hidden from the ABI surface. And in fact, the extension also doesn't require bounds annotations for many of the pointers on the ABI surface. This is based on the observation that most pointers are pointing to a single object, which shouldn't be used for pointer arithmetic and don't even need bounds information in the first place. For this, the extension provides the annotation single, and the compiler makes it default for all pointers except local variables. These are pointers on globals, struct fields, and function prototypes. All right, by combining bounds annotations and wide pointers, bounds safety solves these common challenges in safe C extensions. And there is another real-world challenge, which is to keep source compatibility with standard C. It is important that code adopting the extension still builds with standard C compilers and existing static analysis and code inspection tooling. Also, the extension should be adaptable in shared code, such as library headers and open source projects. Ultimately, the requirement here is to provide bounds annotations that don't introduce new syntax that standard C compilers don't understand. To solve this, we implemented bounds annotations as C-type attributes. These attributes are existing syntax, and so they can be macro-defined. This enables the bounds annotations to be macro-defined to empty when the extension is disabled or not available, and have the code still be valid C. And this way, code adopting bounds safety remains source compatible with C. All right, with this careful design, bounds safety is relatively easy to adopt. Adopting bounds safety is mostly about adding bounds annotations on function prototypes and struct fields where only is necessary. It requires relatively small code changes thanks to implicit bounds annotations. In a very rough approximation, adoption takes 1 hour per 2,000 lines of code, while it's depending on the code base. Currently, the extension only supports the C language. Objective-C and C++ are not yet supported. Bounds-safe code and unsafe code can easily call to each other, and this allows a strategy of incremental adoption. The extension has been adopted in millions of lines of critical software running today on all Apple platforms to make our systems ever more secure. It includes libraries used for secure boot and firmware on the boot paths of all iPhones and Macs in the hands of customers, security critical components of XNU, the kernel that powers billions of devices, built-in image format parsers, such as PNG and GIF parsers, built-in audio codecs for audio content processed by the operating system, including codecs used in FaceTime calls. And these codecs themselves are a couple millions of lines of code base. And there are much more. And this adoption story demonstrates that the programming model is truly effective in real-world applications. Now, I'll explain in more detail how the extension enforces bound safety at the language level. Bound safety enforces the safety rules at the language level, and here are the strategies to achieve this. As we introduced earlier, the programming model prevents out-of-bounds memory access via bounds checking. However, checking the memory access operations alone won't be enough to guarantee bound safety, because pointer arithmetic may allow pointers to go out of bounds and make the bounds information invalid. Thus, the model also prevents pointer arithmetic that are not safe or cannot be proven safe using bounds information. And this generalizes to the problem of maintaining the correctness of bounds annotations, so the compiler can rely on them to do bounds checks, which is what the extension also does. To prevent these unsafe operations, the extension reports compile time errors or warnings, or emit runtime checks and traps if the compiler cannot statically prove safety. But the compiler tries to report problems at compile time as much as possible, so the programmers can identify and fix problems quickly. And it's the bounds annotations that determines what is safe and not safe for a pointer. Now, I'll talk about bounds annotations that the extension offers. And there are bounds annotations that describe bounds information in terms of another value that exists adjacent to the pointer in the interface, such as the counted by annotation in this example. We call this external bounds annotations. But bounds information may be available in some other forms rather than the count value. So bound safety offers several more external bounds annotations to support other common use cases. Let me introduce what they are and their programming model. The counted by annotation indicates the valid index of pointer to be ranged from 0 to count, and the count must be non-negative. So a counted by pointer can only be indexed in a positive direction, in a direction that increases the pointer value. Indexing a counted by pointer in a negative direction will cause a compile time or runtime error. Counted by can also be used inside array bracket to annotate flexible array members. The annotation size by is to support pointers to size list types, such as void star. The size by is similar to counted by, but the argument indicates the byte count rather than the element count. The extension also provides the annotation ended by. This supports bounds information available as a pointer marking the end of bounds, or an idiom known as an end pointer. The compiler keeps bounds annotations correct when a pointer or its bounds information is updated, using compile time restrictions and runtime checks. let me describe how it works using counted by as an example. In this example, function foo gets buffer of 10 elements as an argument. Then inside the function, the buffer gets a new allocation of byte size 4. After this point, the count value, which was 10, is no longer valid. In order to keep the pointer and count values in sync, the model enforces that such related variables are always updated right next to each other. So the compiler reports an error when only the pointer is updated or vice versa. To fix this particular error, you should update the count as well. Now the pointer and count seem to have synchronized updates. But that doesn't mean that the new values are correct. Count should actually be 1 in this case because buffer is a pointer to integer type with byte size 4. Bounds safety prevents such an invalid count values by runtime checks and traps. As you can see in this example, the compiler inserts this check to enforce the new count value doesn't exceed the actual size of the buffer. And interestingly, in this particular example, the arguments of checks are all constants. So the compiler can report this as a compile time error. But for real-world use cases, where the compiler cannot determine the values, it will insert runtime checks. The annotation null terminated is used to secure C strings, pointers and arrays that are null terminated. The compiler ensures that null terminated pointers and arrays are not used to access beyond their null terminators, with compile time restrictions and runtime checks. And most construct pointers are C strings, so the compiler treats them as null terminated by default. As we introduced earlier, the extension supports the annotation single. It can either point to a single object pointer or be a null pointer. And single is default for pointers in function prototypes, struct fields, and globals. A single pointer cannot be indexed in any direction, which will cause a compile time error. And dereferencing a single pointer performs a null check to prevent null pointer dereference. All right, these bounds annotations are just to capture what we believe to be most common idiomatic bounds information available in the APIs. But in this, there will be more to support. And we'd like to work with you all to hear about more use cases. Internal bounds annotations are annotations that allow us to explicitly use a white pointer. When code is not well supported by available external bounds annotations, internal bounds annotations may provide a convenient escape hatch. That said, these annotations should be generally avoided due to ABI and performance implications. The annotation BiDi indexable makes the pointer become a white pointer that has the upper and lower bounds. As mentioned earlier, this is the default for local variables. As the name indicates, BiDi indexable pointers can be indexed in both negative and positive directions. And unlike any other bounds annotations that we introduced earlier, this doesn't change the pointer representation. This does change the pointer representation, and thus it breaks the ABI. So it should be avoided on the ABI surface. Indexable pointers are another white pointer that can be only indexed in a positive direction. Indexable pointers only have an upper bound, So this is more space efficient than binary indexable. But they still change the pointer representation and break the ABI, so should be also avoided on the ABI surface. All right, to support interop with code not adopting bound safety, the annotation unsafe indexable is used to annotate pointers from bounds unsafe code. Unsafe indexable pointers are just like plain C pointers. They can be indexed in any direction without going through bounds checks. Using this annotation in bounds safe code, however, can undermine security guarantees of other bounds safe pointers. So using it should be limited to interoperating unsafe code. Pointers used in system headers are treated as unsafe indexable by default, because programmers cannot normally change their system headers to adopt bounds annotations. In this way, the compiler wouldn't complain to us to add bounds annotations on the system headers. Bounds safe code can call bounds unsafe functions, just like any other function calls, because it preserves ABI. One caveat, though, is that bounds unsafe functions may return a pointer, then the pointer will be treated as unsafe. But the extension doesn't allow directly taking an unsafe pointer to initialize any bounds safe pointer. So for this to work, you need to use this intrinsic function called unsafe_forge BiDi indexable to provide the byte size and create a BiDi indexable pointer. However, there is no guarantee that the size you provided is actually correct. So be careful to not use this in any other purposes. So far, we looked at annotations that bound safety provides. This table summarizes them. It is important to highlight that except those indexables, the pointer annotations do not change the representation of the pointer, hence they are ABI-compatible. Now let's talk about optimization. As bound safety inserts runtime checks, you would expect some performance and code size overhead, especially since many programmers already try to add bounds checks to keep their code safe. Lots of automatic bounds checks might be redundant. Consider this example where the compiler automatically adds bounds checks just before array access to the buffer. Here, the index condition check is correct this time, and it makes the inserted bounds check redundant. To remove such redundant checks, bound safety relies on the LLVM optimization. And this was the primary motivation for the constraint elimination path, which we already introduced in LLVM. The constraint elimination path effectively removes redundant checks. And let me briefly show how it works. The constraint elimination path collects known branch conditions walking through the control flow graph. Based on the known conditions, it identifies and removes redundant checks. In this example, from this loop condition check, the compiler collects the fact that I is ranged between 0 to count inside the loop. Based on this fact, the compiler knows this if condition is always be false. So it simplifies the condition to 0. Consequently, this becomes a dead code, so the subsequent optimization passes will be able to remove it. And interestingly, removing redundant checks means if the code already faithfully contains necessary checks, the bound safety will insert fewer extra checks, and the overhead will be lower. Let me share benchmark results and performance impact on our system. we adopted bound safety on benchmarks to present comparable results. We chose PTR-DIST and Odin benchmark suits from LLVM test suite because they are typically used to test pointer-intensive applications and thus have been used by other related approaches too. We did not adopt two of the benchmarks from this suite due to our current lack of support for idioms intensively used in these two tests. The results are measured on M1 MAC, and all the reported values are in geometric mean. Lines of code changes required to adopt these benchmarks were 2.7%, and 0.2% lines of code use unsafe constructs, mostly to interrupt with system headers. This shows much lower adoption costs compared to prior approaches. The compile time overhead was 11%. The text section overhead was 9.1%. And the runtime overhead was 5.1%. In general, the overhead tends to be lower if the code already has necessary bounds checks. Bound safety has this code size and runtime overhead because it emits runtime checks for cases that are not statically verifiable, with the benefit of lower adoption costs. Also, our backend optimization paths still have some room for improvements to remove more redundant checks. And as a reminder, bound safety has been adapted to software running on Apple platforms, including the iPhones. So we measured overall performance and binary size impact on iOS. It has 0 to 8% binary size increase per project that adopts the extension. And there was no measurable performance and power impact on boot and app launching testing. It has minor performance impact on audio decoding, encoding, which was 1%. The results show that system-level performance cost of bound safety is remarkably low, and the adopters find it absolutely worth paying for the security benefit. All right, before jumping to our conclusion, this work wasn't done on my own. This was a close collaboration with these amazing people across tools, security, and OS teams at Apple, and other incredible collaborators that were not listed in this slide. Thank you all. All right, sorry, I have a conclusion slide. I'm very excited to share that bound safety is coming to the LLVM community. In summary, the bound safety extension is what Apple has been using to secure our security-critical production C code bases. The extension offers ABI-compatibility, incremental adoption, moderate adoption burden, and source compatibility with C. And we are planning to upstream our work and standardize the language model in future. And we'll be providing on RFC very soon. We'll very much appreciate your feedback on the programming model, and we'd love to hear about other potential use cases. And if you are interested we'd love to set up another follow-up roundtable today. Thank you. Now.
So we have time for one or two quick questions. Does anybody have any question for our speaker?
Sorry, could you outline a bit about how does this work compared to, for example, the bound sanitizer, which is the bound checking part of the UB sanitizer?
Right. You mean bounds? So array check inside UBSAN, right? UBSAN array checks are very limited. So that is only for arrays. And when you have, like we said, C pointers don't have bounds information. So yeah, the checks are very limited in UBSAN. And that's not a whole language level enforcement, and UB-sun checks are rather bug finding or mitigation, just to sprinkle around some checks.
Could you possibly flip back to the slide where you mentioned that the pointer and the counted by value need to be updated at the same time or near one another?
Sure. All right, this one.
Yeah, that one. So I'm a little bit curious as to whether there are more restrictions or a more formal definition for what it means to be updated at the same time. So, because for one, the bounds check you inserted happened before the pointer was allocated, reallocated, and before the count value was updated. So there doesn't seem to be an immediate data flow path that you can show between those two, right? So I would have expected something along the lines of having to update the count first, and then using that value, or rather the pointer to that value as part of the reallocation.
Right, that's a great point. So we have some more restrictions because we avoid side effects in between these assignments. So that enforces a certain ordering here. So I think it could be improved. Usability could be improved by providing fixes from the compiler or providing some intrinsic functions that you can use to initialize this as a paired assignments.
Right. Okay.
Thank you.
Thank you.
Any more questions? We do have time for some additional questions.
Hi. It was very exciting. I'm looking forward to wider adoption of this.
Thanks.
And I'm wondering if you have any recipe for the memory pools. For example, in the networking code, you have packets stacked, right, one after another. And so there is formally it's one single array, but those packets might be from different, completely different communication protocols, so it would be still nice to have bounds checks between those. Or, in other case, when you allocate memory from a pre-allocated array for speed, again, the real border lies much further than the actual usable size you would want to enforce.
Right. So I think you are asking the cases where something is allocated somewhere here, and then you will use that pointer farther away, and you are asking how we keep this bounds information and how we can guarantee some safety there.
No, I'm asking about the case where it's more border line towards the type safety. So in a memory pool, you would have a pre-allocated array that is huge, a few gigabytes. And when you request allocations, you don't use malloc, you use the custom allocation function that cuts a chunk of that. And so you would want, ideally, to enforce the bounds of that chunk and not the entire array.
Right. Yeah, that's a great question. So we do provide intra-object bound safety. So the way it works at a high level is that once that is casted to another struct type or some other type, then it will get the bounds related to that type. So you wouldn't get access to what's beyond that you already assigned.
Thank you. That's great.
Thanks.
Any other questions?
Hi, thanks for the great talk. So I'm wondering that with bound safety, you still need the developer or the maintainer to manually add a lot of, like, for example, can't buy these annotations, right? So I'm wondering that, I just guess, like a large part of the code base, they are very, not ancient, but old old code. That what if the maintainers they do not know the exact combine information? How could they add this annotation?
You mean when the maintainer doesn't understand the code base themselves?
Yeah.
Right. So that's that's a tricky case, but so what's nice thing about this model is when you don't have, even though you don't know about code base, when you don't have enough bounds annotations, the code will complain, the compiler will complain about adding some bounds checks, and then programmer can start from there. Okay, this needs some bounds information, and what would be the right bounds for this? So they still need to do some study what should be the right bounds for their code base, but you can do one by one. We provide incremental adoption, so you don't need to do all at once. So I think that way you can study the code and add the bounds annotation incrementally. Does that answer your question?
Yeah, partially. But suppose I'm a maintainer and I'm like the compiler complains on this bound safety. Would it be possible for me to allege, okay, the bound is 10,000? Then would it that like mitigate? I just want to get rid of the compiler error or compiler warning to by like purposely add a large bound to it. For example, I say that this buffer is range 10,000. So the compiler say, okay, all the following access is valid. I just, as a maintainer, as a lazy maintainer, I just want to mitigate, just to avoid the compiler warnings. Would that be possible? For example, as a
You mean
maintainer,
like
I have to be
opting out more fine-grained way rather than the file base?
Yeah, for example, I don't know the exact the count of this buff, but I don't know. My boss asked me to fix that. I just add, okay, this bound is 10,000. Okay, the compiler stop warnings, then everybody is happy. But the code is still running.
Yeah, that's a great question. And so like basically our model is a file by file based incremental adoption, but we also provide pragma that you set another default bounds attributes rather than the single. So which is what we use for system headers. You can set a certain region to have unsafe indexable to be the default pointer attribute. If you set those regions that way, you don't need to annotate inside the region, although you need to do something in order to interact with that code, and that code has bound safety annotations.
Okay.
Does that answer your question?
Yeah. So because of the if I remember correctly, you mentioned that the adoption effort is roughly 1 hour per 2,000 lines of code. So,
yes.
but you said that you have applied this approach on millions lines of code in Apples. I just wonder how many humans you have put onto it.
So like Apple is very secret, so that's like humans are secret here, but you can, I think you can roughly like think it as proportional to the number I gave.
Okay, thank you very much for a great answer.
Thank you.
So one last question.
Given that you need to do source level annotation to make this work, do you already have any experience dealing with open source projects where you want to add annotations, but those projects continue to want to be compiled by other compilers, which do not yet support this? So how do you have a workflow to add support for annotations while still maintaining compatibility with other compilers?
Yeah, that's a great question. So we actually didn't. So we didn't open our model yet. So we didn't put our work to open source yet. but we have a similar experience internally when we adopt certain things, and then that thing also needs to be compiled by other compilers, not our internal compiler. So in order to do that, let's see, let me find. All right, this slide. So in order to do that, bounds annotations are type attributes. So you can macro define. So we provide header that macro define bounds annotations as type attributes, and this is inside if has feature bound safety blah blah. So this is when this feature is disabled, you will get another else block that defines these annotations to empty. So that way, you can apply that to other projects that should be built with other compilers. That way, annotation will be just become nothing. So your code will still remain C code. Does that answer your question?
Okay, so now let's sync our speaker again, and our next talk will start at 10 o'clock.
Thank you.